Dyson spheres are a fairly common proposed end state for super advanced civilizations. The Kardashev scale inherently includes it as a defining factor of a Type 2 civilization. Dyson spheres pop up everywhere in sci-fi, and after atmospheric characterization, Dyson spheres are one of the big things that SETI projects look for most often. I thought I would look at how viable a Dyson sphere actually is. Personally, I don't like them. I think Dyson swarms are far more realistic, or better yet, antimatter annihilation. But I'll do some math to get an idea of whether or not these things are realistic. So ask yourself this: why? Why would a civilization want to make a Dyson sphere? Are you telling me that a civilization advanced enough to be spacefaring and industrialized enough to create an unfathomably large megastructure needs every last joule energy that's coming off a star? What exactly is that civilization going to do with that energy now they have it? They built the thing in the first place, so what are they using to power that building and construction? Seems to me like whatever they were using to do that in the first place should be good enough. But let's say what they were using wasn't good enough. What they were using was just a means to an end. Okay, cool. Once the sphere is built, the civilization has just fundamentally altered its entire solar system. If it's anything like our solar system and the civilization has anything, resembling human emotions, locking away the sun might not be the greatest thing to some people. But let's say instead, these are not real people, these are just like unfeeling, logic worshipping robots. Well, then fine. These are some robots who don't care anything about, seeing a star in their sky. They just want sweet, sweet power. They're still going to run into benign issues like orbital mechanics. You're going to have an issue where it's getting bombarded by lovely sun-grazing comets. These are comets that are on high elliptical orbits, and they take them extremely close to the sun's surface. If you look at pictures from like SOHO or even Parker Solar Probe, you can see these little streaks coming into the frame and going out of the frame. Sometimes they don't even arrive on the other side of the sun because they get destroyed. That's how close they get. But the more immediate issue for this Dyson sphere is going to be literally getting hit by them. Unless there's some way that this sphere is going to be protected by them, it's going to get cracked. Every part of this Dyson sphere has to orbit the star. Unfortunately, orbits in real life are not 2D flat projections on a piece of paper with point masses. If you have a large structure that is an appreciable fraction of the size of the central body, then whichever way the sphere rotates, there will be differences in the tangential velocity. The angular velocity will be the same everywhere, but while you're going to be at orbital velocity around the equator, near the poles, you're just going to be spinning with virtually zero velocity relative to the star. The internal stresses on that structure are going to be enormous. But just for argument's sake, let's say that, these people or these robots, wherever they are, they have just unbelievable metamaterials. They have things that would put carbon nanotubes to shame. This thing can just support itself. They don't really care about orbital mechanics. They just build a sphere and it supports itself. So now for the size, the mass of this space ball. This doesn't go very well. So the sun's radius is around 696 million meters. If we say the sphere is, about a kilometer thick, then the volume of that sphere, is 4/3 pi r cubed. And that works out to a volume of this, the sphere's volume being 2.4 times 10 to the 22nd cubic meters. And if you say you make out of aluminum, then that mass is around 6.5 times 10 to the 25th kilograms, which is over 11 Earth masses. So now that we have, the mass of this thing figured out, we can go into the real interesting parts of it, the energy conversion, the thing that you built this for. It isn't magic, it's thermodynamics. The maximum energy efficiency of a heat engine is finite if the temperature difference between the source and the sink is not infinite. So let's say the Dyson sphere produces power based off heat transfer, and we're going to say it uses like a Carnot cycle heat engine. Because the cosmic microwave background has a temperature, it's around 2.73 Kelvin, it can never be perfectly efficient. So if you do the quick math, you find out that the maximum efficiency of the sphere is only 99.95%, which is really, really high. It's better than anything that we have today. But that leaves, 0.005% of the total energy coming off the sun as waste heat. And so that's going to work out to something like 1.81 times 10 to the 23 watts. And that is still a very, very large number. So if you take that very large number for the waste heat and you try to figure out, how hot is this sphere going to get, you can do some pretty simple calculations just based off the inner surface area, the outer surface area, and how much energy you're putting into it. So the inner surface area and outer surface area, unless you go to a pretty ridiculous number of significant digits, you're not going to see a difference, but there is a tiny one. And so if you take the waste heat coming off the sun and you divide it by the inner surface area, then you get intensity around 7,433 watts per square meter. For reference, Earth, we get around 1,300 to 1,360, somewhere in there, I think, watts per square meter solar intensity. That's 1 AU out. But if you take that number and you plug it into a black body temperature equation, you find that the temperature is going to be at equilibrium around 338 degree Kelvin. That's pretty mundane. It's like 65 degrees centigrade, but it's still, that's going to eat into your efficiency. And so your new temperature efficiency is only going to be 94%. Still really high, but it's, that's almost 6% of your efficiency is now gone. So your new waste heat jumps to 3.6 times 10 to the 26 watts. And so your new effective intensity now jumps again to 92,000 watts. And your new equilibrium temperature jumps to 1,128 Kelvin. And so it kind of snowballs if you have no way to thermally regulate your whole system. So a few caveats here. First, this is assuming that there are no additional radiators or secondary systems to absorb the waste heat or dissipate the waste heat. And second, this will actually take some time to heat up. So if you say, for instance, aluminum, again, is used for construction, we have the kilometer-thick sphere, then that equates to about, 2.44 times 10 to the 27 moles of aluminum. If you do the math, just regular old MCAT, back in the day in high school, you learn about it. That's going to take, 2.1-ish days, just back to the napkin math. But it's kind of just a good baseline to see that, it takes a good long while to heat up to us, but over long time scales, let's say you're going to use this for, centuries, millennia, that's not fast at all. So if you're then going to say, okay, well, how big do I need to make these radiators in order to keep this thing cool? Well, let's say you're shooting for 94% efficiency. That means that your radiators need to be around 1,128 Kelvin when they radiate. And so if you say that they're a black body radiator, they have a perfect emissivity of 1, which isn't actually realistic. You can't get it to be that high. You can get it close though. But let's just say, for sake of the argument, you get it up to 1. Then your radiator size needs to be 3.93 times 10 to the 22nd meters squared. That is a larger surface area than the entire sphere by like 2 orders of magnitude. And even when you subtract out the sphere itself radiating, you still have to have radiators that are 3.9 times 10 to the 21 square meters in size. That's still enormous. So you might think, okay, we could use something like a solar cell farm instead. I would tell you good luck. The efficiencies today are around 50%, and that's for like the very best solar cells. Those are being developed in the lab right now. They aren't actually available to be useful. Typical efficiencies you'll see on like spacecraft solar panels are ranging from 25 to maybe 34%, depending on who you get it from. So the reason they're kind of low is because of the way they work. Solar cells, they function only in a particular band gap of light. And so they aren't able to collect every little bit of light that hits them. And they aren't perfectly efficient in that conversion of, photons energy into electricity. So what you end up having to do in order to get much higher efficiencies is you have to have layered cells. And then eventually you have to have layers of layered cells in order to get higher and higher efficiencies. So you could theoretically have an infinitely large stack, and that would have a very efficient energy conversion. But again, it has to be infinite. And just like with the Carnot cycle heat engines, you aren't going to get perfect efficiency, which still leads to waste heat. And waste heat for Solar cells is a pretty big issue because solar cells are pretty dependent on the temperature that they're operating at. If you get a solar cell really hot, its efficiency drops noticeably. So that is something that you're going to have to take into account even more so with the solar cell solution. You're going to have to really make sure that those things stay at their optimal operating temperature. So those are just some of the main reasons why I think a Dyson Sphere is a horrible idea, quite frankly. I would say again that Dyson Swarms are far more practical. This argument also doesn't hold up perfectly if you use something like a white dwarf. I think it's much more practical to do an actual Dyson Sphere around a white dwarf because it's so much smaller volumetrically. And it gives off a pretty large amount of energy for that small size. I think that's very doable. That does assume that you have something like interstellar travel. So yeah, hope somebody realizes that Dyson Spheres aren't the greatest things in the world. They're kind of ridiculous when you think about them a little bit. This math isn't, the end all be all. It's pretty simple. There are definitely ways to make them better, but at the end of the day, they just aren't as practical as some of the other solutions. Maybe somebody's gonna tell me I'm wrong. I don't care personally, but hey, go use black hole annihilation. It's just better anyways.